welcome to the Thursday morning session, and it's great to have Yingyu Liang talking about non-negative matrix factorization.
Okay, so this is joint work with Yingyu Li and Andrei Ristetsky, both are students from Princeton University. So let's begin to consider recent advances in machine learning applications. So we have seen significant advances along these machine learning applications, such as dictionary learning, matrix completion, and especially deep learning, and a lot of new things happening. Along with these advances, we see a lot of non-convex problems. For example, like all those applications listed here, I mean, in their general form, just non-convex problem, although there is like convex relaxation, but usually the problem is formulated in a non-convex way. So these problems, in their general form, are just hard to solve, but it seems that the practical instances are not so bad. So basically people are getting used to formulate a problem in a non-convex way and just solve them by some heuristic and get good results. So they are not scared by this non-convexity. And especially often we use some simple method to get some local improvement. By that I mean this simple method often has multiple iterations, and at each iteration we just look at the information at the current solution and try to get some local improvement. So the most commonly used one is so-called gradient descent, and its variants such as stochastic gradient descent. So suppose we have some objective function and we want to minimize it. Then we can just take the gradient at the current solution and move a little bit along the negative direction of the gradient. So this is a very basic algorithm, but it works really well. So it's the basis for example, the deep learning. And another approach is this so-called alternating update method. So usually the problem has two blocks of variables that you need to determine. So you fix one of them, you update the other, and then you fix the other and update the first one, and repeat this procedure. The advantage is that many problems, if you fix one of the variables, updating the other is quite easy. So this is very popular in practice for such kind of problem, if they have the structure I just mentioned. So this is a concrete example, matrix factorization. We are given a matrix Y, and we want to find two matrices, usually low rank. And then we want Y equal to the product of A times X. So then after doing some initialization, we can just say fix A and update X. Basically like find the best X that fit the current A. And then we fix X and then find the best A that we can get. So it's kind of like some best response dynamics. So it turns out that this two very simple method or heuristic works really well for a wide family of problems, including like those I listed on the first line. But generally, there's no theoretical guarantee. So the interesting questions are when and why do such algorithms actually work for the hard problems. So the goal here is first, make some natural and clean assumption about the practical instances, and then we show that these simple methods can actually recover what we want.
Excuse me?
Right.
Yeah. Ask a question. So when you say it works,
oh yeah.
It's fast because you stop it after like 10 minutes, or gives a good value solution because you compare it to something, or?
Yeah, that's a good question. So basically, if you have an objective function, by works, I mean, you can minimize, you can get a solution that is close to the global optimal, either in objective function or in the solution.
How do you know the global optimal? Because if you know the global optimum, probably you have a different algorithm that works better.
Yeah, that's a good question. So basically, for some of the problems, you may be able to show that all the local optimals are just global optimal.
Like, you mean or
Yeah, proving. So for example, like matrix completion under some assumption like incoherence and random. Teng Yu is not here. Yeah. So basically, for some problems, you can show that. Another way to show that it works is that you assume some so-called generative model, and in which you actually have a ground truth. So you want that ground truth. You don't care about the objective function. You care about the ground truth. So what you want to show is that this algorithm, given the data from that distribution, after a while, you actually get close to the underlying ground truth. So yeah, yeah.
I mean, this is by simulation.
I mean,
On simulated data, it's not on real data, the generative model, yeah.
Yeah, on generative model, if you want to empirically verify, usually you simulate, right? Because you have the generative model, you can just generate data. But our hope is that the generative model is natural in the sense that it maybe is close to the actual data distribution that we observe in practice. So that is the hope. Yeah. Okay, so this work is about analyzing alternating update for non-negative matrix factorization. So then what is non-negative matrix factorization? It's just a factorization problem under the additional requirement that the entries of the factorized matrices should be non-negative. So in some cases, you only require the entries of X is non-negative, but for simplicity, let's just say we required both are non-negative. So this leads to a non-convex problem. It's a important theoretical concept. Basically, it relates to non-negative rank and like log rank conjecture in communication complexity. But here we care more about its application in machine learning. It has many applications here. The typical one, is the topic modeling, which is a mixture model for analyzing data such as text, images, or even networks and many other type of algorithm. So here in this setting, the Y matrix, so let's say each column of Y matrix corresponds to a document, and each row corresponds to some word. So each column is basically the word distribution in this particular document. For example, like this document has like 0.04 fraction being the word rain. It's just a synthetic example. And this matrix A is called a topic matrix. Each column is called a topic. Basically, it's just a distribution over the words. But it's meaningful in the sense that it corresponds to some concept. For example, like this topic weather has a large probability on this word rain and has small probability over some other not so related words like soccer, physics, and things like that. So this is the topic matrix. And this X matrix is each column of it corresponds to a document, and it's just mixing coefficients of the topics in this particular document. Let's say this document has 0.2 fraction of the topic weather and has 0.8 fraction of the topic science. So Y equals A times X basically means that by mixing the distribution of the topics, you get the distribution of the words in this document. So you can imagine that by discovering the topics among a large set of documents, you can get an overview of the themes of this document. So it's very useful and popular in social science and also like information retrieval and many areas. Okay, another example comes from computer vision. So you apply non-negative matrix factorization on images. Say this example is coming from a Nature paper. So you are given some images about human faces. You want to find these so-called pattern images. So each small square is actually an image of the same size as this original face image. So we shrink it because we need to have space. So then you want to find a bunch of pattern images. And then by a non-negative linear mixture of these pattern images, you can recover the face image. So by piecing them up, you can get this face image. So now you don't know this pattern image, you don't know the weights. You are given this a bunch of images. So each image is just a column in our matrix Y. Then you run this non-negative matrix factorization using alternating update rules. Then you can discover some interesting patterns. Some of the images, let's say this might correspond to the mouth on human faces, and some others might correspond to eyebrows and things like that. So you can get a par-based representation of human faces. So this is another example. So it also has many other applications like analyzing networks and like information retrieval and things like that. But as similar to some other machine learning problems, usually we have a large gap between the worst case bound and what happens in practice. So Aurora, Gu, Kanan, and Moitroy show that there is no sub-exponential algorithm assuming ETH, and they also give an algorithm running exponential in K. K is the number of columns in the matrix A. So you can see that this basically is impractical for any practical use. But what happens in practice is just this heuristic suggested by the computer vision guys, Li and Song, that you can just do alternating update. After setting an initialization, so usually set by some human experts on this data set, and then you can just repeat the two steps. You compute X from A, you compute A based on X. So I'll be more specific about this algorithm later on. But this is just a simple algorithm. You can just run and get very good results. So this large gap just requires some analysis for practical instance rather than worst case instance. So how do you model practical instance for machine learning applications? So the most common way to do so is so-called generative model, where you assume there's a ground truth solution. So here, let's say we have a ground truth A star matrix, and then you assume that the data is generated from a distribution defined based on this ground truth. So it has some information about the ground truth, and you want to discover the ground truth based on the data. So another approach to do beyond worst case analysis for machine learning problems is so-called warm star. Basically, it's assuming the initialization is not far away from this ground truth. For example, like here, is not far away from the ground truth. This is motivated by the fact that the initialization is often set by some human experts. So it's reasonable to assume that is better than just random guessing. So you can assume that it's not too far away. Okay, so what do we know about NMF? So this paper proposed the so-called separability assumption motivated by topic modeling. The assumption says that each topic, basically each column of the matrix A has a so-called anchor word. Well, what is an anchor word? It's just a word that appears in this particular topic, but do not appear in any other topics. So under such kind of assumption, there exists efficient algorithm for this problem, and you can just run it, and actually there's a lot of subsequent work along this line, and there are very practical algorithms. Another related work is by Avashthi and Ristetsky. They analyze this variation inference method. Basically, it's an alternating update method for topic modeling. They alternating over A and X, try to minimizing the KL divergence between the columns of Y and the columns of A times X. So in this work, basically it requires quite strong assumption on A and also a warm star, depending on the dynamic range of the entries in the matrix A, so which is not so realistic. So. And also, the assumptions may not hold for some other type of data beyond text. For example, like computer vision, the assumption is a little bit off. So the interesting question is, can we show provable guarantee of the simple method under more general assumption? So now let's turn to our work. I will describe the model algorithm and then provide the results and an overview of the analysis. So this is our generative model. We just assume that each column of Y, basically a data point, is IID example from this distribution, A star times X star. Here, A star is a deterministic ground truth matrix, and X star is a random variable, a vector. So then we can, for simplicity, let's assume that we have infinite data. And then the only assumption about the matrix A star is linear independence. So this is very mild condition. First of all, is a generalization of the angle word condition. And also, we kind of expect the columns of A to be convex independent, otherwise is even non-identifiable in the sense that you may have like infinite number of A that satisfy the data. So although there's a difference between linear independence and convex independence, but we don't know how to make use of that, so we just assume linear independence. Now we also assume some distribution on the random vector X star. We assume that the coordinates are independent. So this is the key assumption. And we also assume that it's just 0, 1. It's 1 with certain probability as 0 otherwise. So in expectation, this is a vector with S non-zero entries being 1 and all the others being 0. So just a very simple model. So our analysis generalized to some other more general assumptions, but this is sufficient for demonstrating our intuition.
Bruce,
yeah.
That's the question.
Okay.
Doesn't this look a lot like the sparse coding setting as well? Because X is a sparse vector and A is...
Oh, our results generalized to non-sparse vectors. So sparsity is not the key assumption here. But the independence is the key assumption. So it's also called non-negative ICA, independent component analysis, in the empirical papers. But we don't find any theoretical analysis for that, so we still, yeah.
So S I should think of as being somewhat close to K, order K or something?
Right, you can think of it as that. It can be sparse and it can be non-sparse, but it doesn't matter.
So if S was 1, this would be easy. K is the number of, K is the size?
The number of columns in A.
So if S was 1, then you would be seeing some columns of A in your Y.
Right.
So that would be the
Yeah, that would be the easy case. Okay, let's continue. So this is our algorithm. We have some parameters that I will explain later, but basically it's just the alternating update. In the first step, we compute x. We call it decoding, just from like computer vision literature. Basically, it means that for each example y, you try to get the corresponding x. How do you get it? You just multiply it by the pseudo-inverse of the current solution. That's why we need linear independence. And then we pass it through a nonlinear function, looks like this, and then get x. So what is the nonlinear function? It applies to each coordinate of the input vector. And for each coordinate, if it's smaller than alpha, then sets it to 0. Otherwise, just keep the original value. So this is called rectified linear unit ReLU in deep learning. And it turns out it's crucial for proving the convergence result of, in our setting. So there might be some connection to that, but we don't know.
Sorry, I'm not quite following. So how is the loop dependent on t, and what is a? Could you explain one more time?
Oh, okay. So here I just omit the subscript t. So let's say because for simplicity, we assume that you have infinite data.
Okay.
So each time you just sample a lot of y. And then for each y, you use the current solution. Let's say this is AT. You use the pseudo-inverse of the current solution AT. And then you get the decoding. And then I will use these decodings in updating AT to AT plus 1, let's say. Right.
I'm not sure you remember the notation. He's factoring y into a times x.
Right. But yeah, I wasn't sure what was happening. And I guess the algorithm's not completely there yet.
No, he hasn't told you that.
No, the dagger is also a T. The A dagger.
There's a
Also.
step how you go from x to
Yeah, he hasn't told you that.
Yeah. Oh, okay. Yeah. So there should be a superscript t or subscript t inside this dagger. But yeah. So. Okay. After getting the decoding, we just do the update. It's also quite simple. We just compute some direction and then move along that direction. So what the direction is just the expectation over y minus y prime times x minus x prime transpose. So this is a vector, this is a row vector. So you get a matrix out of this. So here y and y prime are two independent examples. And x prime are their corresponding decodings. So we need to use some polynomial number of examples, but here I just take expectation for simplicity.
One more question. That y has nothing to do with the y on the previous line, right?
You mean this y? So you can think of it as let's say m copies and m examples y1 up to ym, right? So we just use the first half as this, the second half as this. Let's see.
Wait, that's confusing. Those are just two independent examples.
Right.
What's the half?
Okay, so let's say we draw two sets of examples.
Oh.
Yeah. So the first set of example we decode it in this way. The second set we also decode in this way, and then we use the first set as y, the second set as y prime, and then we get it.
You need to use fresh samples for each
For analysis, yeah, because it simplifies things a lot. But it's just logarithmic iteration, so it's okay. With some extra work, you may be able to show that you don't need independent sample, but it just complicates things.
Yeah, but I mean, in the matrix completion setting, which is kind of similar, it was difficult to get rid of this requirement.
Oh, so here is slightly different. It's not so difficult to get rid of the fresh sample. Okay. So this completes the specification of our algorithm. Now let's do some sanity check. Suppose we have the ground truth. What would happen? Let's first check the decoding. So if you plug in the pseudo-inverse, just cancels out the ground truth, and then you get X star. Because it's non-negative, so ReLU doesn't do anything. So you get the ground truth, X star.
If alpha is 0.
Alpha. So you can think of alpha has a small constant between 0 and 1. So, yeah, so I didn't specify. Yeah. Sorry. Yeah. Is that okay? Yeah. Okay. Okay, now let's check the update. So in this case, if we plug this in and also plug the true decoding, then we get that it's proportion to A star. So you are moving along the right direction. But there's some scaling here, so we need to have different step sizes to take into account the scaling issue. But anyway, the update direction is just the ground truth, just pointing to the ground truth. So this seems reasonable. Okay, but it turns out that because we only assume linear independence of the columns of A, so if the matrix A is far away from the ground truth, basically we cannot say anything about the algorithm. So weird things can happen. We have some examples showing that you can get very weird things. So for simplicity, we just assume that the initialization is close to the ground truth up to a constant arrow. What do I mean by arrow here? Basically it means that the columns of A is a linear combination of the columns in A star. And in particular is A times A star times a large diagonal matrix plus a small off diagonal matrix. So to parse what this means, let's look at a column of A. Then if you expand this out, basically means it's a combination of the corresponding ground truth column we want, AI star, and some components from other columns in A star. So the assumption basically means that you have a large fraction along the one that you want, and all the others are just a constant. Yeah, just takes up a small constant fraction. So we can relax this a little bit, but we cannot make it larger than a half. So beyond a half, it's not even like identifiable thing, and weird things happen. So now under these three assumptions, we can have this clean theorem saying that after log of 1 over epsilon iterations, you get the arrow to be epsilon. So here we still maintain this to be 1 minus L, but if you know that the columns of the ground truth has column norm 1, so you can just do normalization, and then after normalization you can get this to be 1 minus order epsilon. So basically it just means then you can get epsilon arrow after like logarithm iterations.
Can you use this assumption to sort of decode X? Like you get a Y, so you look at the columns of your current guess of A that have the component, and you keep those, and then you decode X, no?
In this particular simple generative model, yes. But it turns out that the same intuition can be generalized to the case that you might not even be able to recover the support of X star.
This is for the non-sparse case?
Yeah, for the sparse case with 0 and 1, it's easy to recover the support and things like that. But the intuition here that I'm going to describe applies to more general setting that you might not be able to recover the support even.
So I'm asking, is that the non-sparse case or which case?
Yeah, non-sparse case.
Yeah.
Yeah, right. Okay, so how do we analyze? So it turns out that this expression is the beginning of our analysis. So we just try to show the method can maintain large sigma and at the same time just make E, the arrow matrix E decrease. So we need to have some measurement to measure the size of this arrow matrix. So we define this potential function, which is basically take the norm of the positive part of E, take the norm of the negative part, and do a weighted combination. So it seems a very weird potential function, but anyway, if we can show these two things, we can prove the theorem, right? So now let's focus on this arrow matrix and this potential function to see why we want this weird thing here. Why not just use the norm of the arrow matrix as a whole? It turns out that it's basically because the ReLU non-linear function treats the positive part and the negative part in different ways. It can remove the negative noise, but it cannot remove the positive noise. So you need to treat the two parts in two different ways. Okay, to be more specific, now let's first look at the decoding. Let's simplify things by assuming that the sigma matrix is just the identity because we always keep it to close to 1. So let's just say it's identity. Under this assumption, let's see how the arrow matrix is changed by the update rule. Let's first look at the decoding. If we plug the expression of A into the decoding rule, then basically it's just this expression. You take the inverse of identity plus the arrow matrix and times x star. So if we do a Taylor expansion, so it looks like this. So we also need to handle the higher order term. It's not so easy to handle, but the intuition is that it consists the ground truth that we want, and also some arrow related to this arrow matrix, right? So let's say some noise related to this arrow matrix. Okay, so you can imagine that the nonlinear function, the ReLU here, is just to remove this noise. Okay, now let's look at the entries of this x star minus E times x star. So it looks like this. The green bars stands for, say, the non-zero entries in the ground truth x star. And the yellow ones are just the noise introduced by this second term. So it basically looks like something like this. And it turns out that although the total amount of noise is large, they are spread out. So you can imagine, if you set this alpha properly, you can remove a large fraction of the noise while maintaining a large fraction of this ground truth that you want. So you get a much cleaner version after doing this ReLU function. So this is basically the why we need ReLU. Okay.
If alpha was 0, you would not remove the positive noise.
Yes. So we.
Problem? If alpha can't be 0,
Yeah, it can't be 0.
you can't remove positive noise adds up for if that happens.
If you have positive, yeah, it has positive noise, right? So sometimes you have positive noise that can, for example, like you have a positive noise into this. So basically ReLU cannot like have a good effect on that. That's why later on we need a delicate potential function.
Is there some relation between alpha and S? So if you knew that X was going to be very sparse, then maybe you want to...
Right. So in this simplifying, so in a more general setting, alpha has depends on quite a few things, but there is this one. In this simplified setting, yeah, I think it. I didn't did a calculation, but yeah, it also depends on the sparsity. But let's see. Yeah, I think it depends on.
So if you don't know the sparsity, then you...
Right, so basically this is something that we need to think more about. Basically because our guarantee is something like this is a set of parameters alpha and step size eta 1, eta 2, such that you can get this thing, but yeah. Oh, okay. Yeah, I'm getting close. So after doing the decoding, you can plug into this and do a bunch of calculation that is not so interesting. But at the end of the day, the update on the arrow matrix looks like this. So this is the original arrow matrix, I mean, in the previous iteration. And after one update, you just modify by moving along this update direction. And this update direction...
What's the green and the brown?
Oh, yeah. The green stands for the positive entries in arrow matrix, and the yellow one stands for the negative. Of course, I just made them into two parts, but they can be like scattering around, but just for simplicity. And it turns out that the update direction, so this delta matrix here, has a very specific form. You first take the original arrow matrix E, transpose it, and then you scale down the positive entries by a small constant. Why? Basically, it's because, as I said, if you have a positive entry here, its effect on the decoding, let's say, on the decoding is contributing a negative noise. So you can imagine that it kind of like can be, most of the time it can be like threshold by this this ReLU function. So, right, this is, but for the other parts, the negative entries, you don't have this nice property. But it turns out that this small constant on this positive part are sufficient. So basically, if you set eta 1 and eta 2 properly, you can make sure that the sigma matrix stays close to 1. And you can also make sure that this negative, this positive part will not be blow up too much by this negative part. And on the other hand, the negative parts would be decreased because of this small constant. So then by a weighted combination, you can show that this actually decreased. But if you just use the norm of the arrow matrix as whole and do not use the weighted combination, it can actually sometimes increase a little bit. But if you consider this weighted combination, then you can show that it always decreases. So then we get our result. Okay, so this kind of analysis can also be applied to some other more general setting. For example, we have noise to each column of Y. This is basically because you can handle this kind of noise in the same way as before. You can imagine that you're just adding an additional noise term here, and then you can argue using the previous intuition. So it turns out that you can tolerate large adversarial noise, and if the noise is zero mean, the noise can be a square root k larger than the L1 norm of the signal. But so this is very strong denoising effect by the ReLU.
So it's adversarial, so it's not IID or?
Yeah, no assumption. I mean, in this setting, is no assumption. Yeah, if you have zero mean, then you can. It's basically because this and the coupling of the two parts you can use this analysis to show that you don't need much assumption. But the key assumption is that the noise should be spread out across different entries. So I should say that it's not totally adversary, but it's adversary on each entry. So basically you have an upper bound on each entry of this noise vector. But it can be any distribution entry-wise. So it can also be used in some other distribution of the X star. We only need to satisfy some moment condition about the first moment and second moment. So it's quite general. But we still need the coordinates to be independent of each other. Why? Because when we from this step, this decoding, to showing this, basically you need the independence of the coordinates so that you get a lot of cancellation here. But that's the high-level intuition. So let's summarize. Basically, we have the good analysis of this problem under the assumption that is fair in mind, but we still need a warm star. And then we discovered the very strong denoising effect of the red loop. So it can make use of the non-negativity constraint in this particular problem. So it's, Okay? Yeah, I think that's all. Okay.
Maybe a quick question while the next speaker is setting up.
Do you need to know alpha in advance, or you just do binary search, or can you set according to the error?
Yeah, indeed, you can do binary search. Right? But indeed, our algorithm need to know the alpha in advance. So you can do some estimation, but we need.